Hello everyone and welcome to the 15th lecture in the course on solar photovoltaic system design. So in the last lecture we looked at the phenomena of light absorption in a solar cell and we understood how solar cell absorbs light of different wavelengths at different depths, and we saw how infrared radiation actually is absorbed much deeper in the solar cell while the ultraviolet and the visible region is absorbed quite in the upper regions. So today we will look at the light absorption phenomena in little more detail and we'll try to understand few more related terms. So in today's lecture we will be looking at absorption efficiency and quantum efficiency and how these two terms relate to the understanding of absorption of light in a solar cell. So a similar diagram we looked at in the last class, but then that was a simplified version where there was some incident radiation which was incident on the solar cell surface, and then as it entered the solar cell, the absorption intensity was decaying exponentially. But here we have added two more terms if you see here. So one is the reflected radiation ER. So E naught is the total incident radiation and there is some reflection happening at the interface of the solar cell. So ER is the reflected radiation, and then out of E naught, ER gets reflected, E1 is what enters the solar cell from the top surface. And then similar to what we discussed last class, that this incident radiation which enters the solar cell, its intensity starts decaying exponentially as the radiation travels deeper and deeper in the solar cell. And finally at the bottom end of the solar cell, the radiation has decayed down to a value of E2. So it starts with E1 at the top surface and decays down to E2. So that is the situation we are considering now. So we will be taking the reflection factor also into account, and we define here the reflection factor R as ER by E naught. So out of the total incident radiation E naught, ER is what has been reflected. So that is the idea. ER is the portion of the incident radiation E naught that is reflected at the surface. So now if I want to do the mathematical formulation of this radiation or the incident radiation and its balance inside the solar cell, I can say that the E naught was the incident radiation, ER is the reflected radiation, and therefore the portion of radiation which is penetrating into the solar cell so this portion which is penetrating into the solar cell, I am indicating that by symbol E1, and that E1 is nothing but 1 minus R times E naught. Now this particular radiation E1, it starts decaying exponentially as we go deeper and deeper in the solar cell. The radiation intensity starts decaying exponentially such that at the bottom end of the cell, where we are saying your depth of the solar cell is D, at the bottom end we are calling this as E2. So we can give this E2, this formulation E2 as your radiation at x equal to D, and this is equal to E1 e to the power minus alpha D. And if I look at the absorbed radiation, the radiation which is absorbed in the solar cell, that will be nothing but the incident radiation, basically the radiation which penetrated inside the solar cell E1 minus E2, because ER had already got reflected at the top surface, E1 entered the solar cell, and out of that E2 is still remaining at the bottom of the solar cell. So this is the E2 is the irradiation at the bottom end. So if E1 was initially what entered, E2 is what is still remaining, then the absorbed radiation is nothing but E1 minus E2. And now we define the absorption efficiency. We indicate this by symbol eta subscript ABS, and it is defined as the ratio of the number of absorbed photons to the number of photons incident from outside. So, that is how we define the absorption efficiency, the ratio of number of absorbed photons to the number of photons incident from the outside. So, I can write eta abs is nothing but number of absorbed photons divided by the number of incident photons, and this I can write as, let us say, NPH ABS divided by NPH, where we understand that NPH ABS, or the number of absorbed photons, is nothing but it is dependent on basically the intensity of radiation which has been absorbed in the solar cell, divided by the NPH is dependent on the total incident radiation intensity, or in other words we can say this is nothing but E1 minus E2 divided by E naught. So, that is my absorption efficiency. However, we would like to simplify it a little more, because still it is little vague in terms of E1 and E2. So, let us try and simplify this using this formulation. So, as we saw, E2 we have defined as E1 e to the power minus alpha d. Therefore, I can write eta abs in this form, E1 minus E1 e to the power minus alpha d divided by E naught, or in other words I can say E1 1 minus e to the power minus alpha d divided by E naught. And further, E1 is the radiation which entered the solar cell from the top surface, and that we have already seen, we can write that as E naught 1 minus R, and the remaining terms come as it is. And therefore, my eta abs, or absorption efficiency, in simple terms I can write that as 1 minus R into 1 minus e to the power minus alpha d. So, that is my absorption efficiency, where we understand that R is nothing but the reflection factor, alpha is the absorption coefficient, and d is the depth of the solar cell. Now, this absorption efficiency simply indicates that out of the total incident photons, how many photons have been absorbed. And if I want to increase this factor, actually it is quite possible to make the absorption efficiency as close to 100 as much as possible. So, we can have eta abs, or the absorption efficiency in percentage terms, pretty close to 100%. For that we need to do two things. One is that we need to reduce the reflection at the surface. So, I need to cut down the reflection. If I cut down the reflection, if I make the reflection very close to 0, then this factor approaches 1. On the other hand, to make this factor approach 1, what I need to do is that the cell thickness I need to adjust. So, the cell thickness should be taken such that for x equal to d, almost no photons are left. So, by controlling these two phenomena, the reflection and the depth of the solar cell, we can make the absorption efficiency pretty close to 100%. However, there is a word of caution here, because if you relate to what we discussed earlier, in different depths of the solar cell, different phenomena is happening in terms of absorption of the photons and then creation of electron hole pairs, and then what happens with those electron hole pairs. So, as we discussed, if you go too much deep into the solar cell, maybe those electron hole pairs might not be so productive. However, there is the concept of back surface field also, which increases the productivity of the bottom layer of the solar cell. So, overall judicious choice of the depth of the solar cell needs to be made, taking all these factors into account. So, that is the concept of absorption efficiency. Now, a related concept is the concept of quantum efficiency. So, let us look at that particular concept as well. So, quantum efficiency, this is a slightly different way of looking at the efficiency of a solar cell. These are like different layers of talking about the efficiency of a solar cell. We are still not talking about the actual final efficiency of the solar cell in terms of output versus input. We are just talking about different aspects. So, absorption efficiency just talked about the efficiency of absorbing the radiation in the solar cell. So, out of the total incident radiation, how much is being absorbed? Something got reflected, something which entered the solar cell, out of that how much we were able to absorb. That is the only thing which we are capturing in absorption efficiency. Quantum efficiency goes a little step further. So, out of all the absorbed photons, not every photon might produce the effective electron hole pair. So, the idea is that even if absorption efficiency eta ABS equal to 100%, let us say, which is quite possible theoretically and practically also we can go very close to 100%. Still, not all electron hole pairs would contribute to the photocurrent. So, that is something important to look at. Out of all the photons which are incident, first thing is that you are absorbing some portion of the photons. So, that is the absorption efficiency. Now, out of these absorbed photons, the first condition, very first condition is that your photon energy EPH should be greater than or equal to the band gap energy EG. Only when this condition is satisfied, that my photon has energy more than the band gap energy, this will lead to the creation of electron hole pair. So, first phenomena is that out of all the absorbed photons, some might not be having that much energy to lead to the creation of this electron hole pair. Now, those photons which have that energy, required energy more than the band gap energy, and they created the electron hole pair, out of all those created electron hole pairs, not all the electron hole pairs might not contribute to photocurrent. And the reason why that is there, why we are saying that not all electron hole pairs would contribute to photocurrent, is because of recombination, because there are recombination phenomena also in the solar cell we discussed earlier. So, due to these two factors, one is that not every photon has energy more than the band gap. Second is that there is an effect of recombination. So, many of the generated electron hole pairs might not actually contribute to the final photocurrent. So, due to these two phenomena, the quantum efficiency will actually be lower than the absorption efficiency. So, for this reason we can define our quantum efficiency in this form. So, quantum efficiency, again there are two ways of defining. One is the external quantum efficiency. So, its external quantum efficiency we define as the ratio of number of usable electron hole pairs divided by the number of impinging photons, or in other words we can write this as number of usable electron hole pairs I am indicated by NEHP and divided by the number of photons. So, this is the external quantum efficiency. And then there is a second version of quantum efficiency as well. This is also known, external quantum efficiency in short is known as EQE. Another version is known as the internal quantum efficiency. Which we can indicate as IQE, and the definition is slightly different. So, here what we are saying is that this is defined as your number of usable electron hole pairs divided by number of photons penetrating into the solar cell. So, basically what I am doing here in the second one, internal quantum efficiency, is that I am leaving out the reflected photons, only the photons which have entered into the solar cell, those I am taking. So, this I am calling as NEHP divided by NPH penetrating only. So, basically the reflected photons I am leaving out. So, in other words, I can say that my eta internal, the internal quantum efficiency, is equal to eta external quantum efficiency divided by 1 minus R. So, whatever is the reflected, suppose 10% is getting reflected. So, 1 minus R 0.9. So, I will divide the eta external by 0.9. So, my internal quantum efficiency will always be more than the external quantum efficiency, greater than or equal to. If reflection is 0, then it becomes equal, but if any value of reflection is there, then my internal quantum efficiency will be more than the external quantum efficiency, due to the simple fact that in internal quantum efficiency I am not accounting for the photons which have not entered into the solar cell. Anything which has got reflected, those I am removing from the denominator. I am only taking the number of photons which have penetrated into the solar cell. Now, here everything needs to be taken with a pinch of salt, because there was one very interesting discussion I had with my students when I was teaching this in the class, and someone came up with a very interesting idea. They said that, okay, I want to increase the internal quantum efficiency. So, there are two ways I can increase. One option is that I can increase the external quantum efficiency, and second way is that, let us say if I increase the reflection. So, if I increase R, as you can see here, so let us say if I make R as 0.2, then it becomes, internal quantum efficiency becomes 5 by 4 times of the external quantum efficiency. On the other hand, if I increase R further, I make R as 0.5, 50% reflection happening, then eta internal would be 2 times of eta external. So, a student came up with that logic. So, and they said that, can we go ahead like that? So, that is actually a fallacy. That is not really the correct concept. We should be careful about how we look at things. See what is happening here, because physically what is happening, the physical phenomena in the solar cell is only this one. You are having some photons incident on the solar cell. Out of those impinging photons, you are producing some electron hole pairs. So, this is the actual physical phenomena which is happening. Internal quantum efficiency is just another way of accounting how you are accounting for the efficiency. So, in internal quantum efficiency, the reflected photons you are leaving out, you are saying that, okay, what has entered inside the solar cell, those I am taking in the denominator. So, here you are just changing the way of accounting for the efficiency, but the physical phenomena is not changing. The physical phenomena actually corresponds to external quantum efficiency. So, therefore, the logic that we can increase the reflected radiation or the reflected coefficient, and we can, that is how you can say quoting higher value of internal quantum efficiency, does not have any meaning. Basically, it is just a way of accounting. It just shows that how much reflection is happening in the solar cell, and reflection is an undesirable phenomena. Ideally, we would like to have as much low as possible. If possible, ideally we would like to have equal to 0, and ideally we would like to have internal quantum efficiency equal to external quantum efficiency. So, basically what I would like to do is that I would like to increase the external quantum efficiency as much as possible, and I would like to reduce the reflection as much as possible, so that I move towards this condition. That is my ideal condition, that my internal quantum efficiency is equal to the external quantum efficiency. So, we have to be little careful when we look at the equations and the formulas. So, before we end today's class, let us look at a numerical to understand the concept of quantum efficiency in little more detail. So, this is just a very simple, I mean the concept is quite rigorous, but I have put a simple representation of that concept so that we can solve it as a numerical problem. So, as you can see here on the right hand side there is the spectrum of the solar radiation given. So, you have the spectral intensity graph for radiation incident on the solar cell, and you can see in this graph that yellow region. So, yellow region is the sunlight without atmospheric absorption, basically that is the solar spectrum outside the Earth's atmosphere. And then as we discussed that when the radiation passes through the Earth's atmosphere, there are different phenomena like absorption, scattering and reflection which happen. So, finally what you get on the Earth's surface is this red one. So, that is what is shown here as the sunlight at sea level. So, the red spectrum, red colored spectrum, that is what is the spectrum of solar radiation on the Earth's surface. Now, I have put here on the left hand side for ease of calculation simplified approximation of this useful portion of the solar spectrum of solar cell. So, the spectrum of solar cell, and here I am taking just the visible and the infrared region, because ultraviolet region also mostly it will be cut out by the your ozone layer in the atmosphere. Mainly it is the visible and the infrared region, and then in that region also I have just taken some sample wavelengths. So, I am just looking at a simplified approximation of the solar spectrum, and I will use for this problem this particular graph. So, suppose I am saying that there are these wavelengths from 400 to 1100 nanometer, and their spectral intensity is given like this, you know. So, I am taking again, I am taking your discrete values, quantized values. So, I am saying that around the mean of 400, that means from 375 to 425 nanometer, the spectral intensity is, let us say, this value, 1 watt per meter square per nanometer. Then from 425 to 475, the value is around 1.15 watt per meter square per nanometer, like that. From 475 to 525, the value is around 1.25 watt per meter square per nanometer, like that. So, the spectral intensity values in watt per meter square per nanometer, and I am just making a simplified assumption for ease of calculation, because we want to do simple numerical manually. Practically, if you want to do this in the best possible way with the best accuracy, you should do a computer simulation or a programming approach, where you take the spectral intensity, you read the spectral intensity at each wavelength, you read from this graph, you can read each value, spectral intensity value at each value of the lambda, and then you can proceed with those values in a computer program. Right now, I am just taking a simplified assumption for illustrating the concept for a numerical problem. So, I have assumed that there are only these quantized wavelengths. So, every 50 nanometer apart, I am taking these wavelengths only, and I am also assuming that the spectral irradiation or the spectral intensity in watt per meter square per nanometer is constant over a band of 50 nanometer wavelength, like that. So, assuming this particular spectrum and solar cell area of 4 centimeter square, we consider that this solar cell produces a current of 0.05 amperes, and we have to find out the eta external. What is the external quantum efficiency? So, that is the problem at hand. So, let us look at a quick solution of this before we end today's class. So, the best approach for solving this would be tabular format. So, what you can do is that you can create a table of this sort. You can have lambda values here. So, you can have lambda in the first column, and we are taking these discrete values only 400, 450, 500, 550, 600, 650, 700, 750, 800, 850, 900, 950, 1000, 1050 and 1100. So, those are the lambda values. Then we read the spectral intensity values from the graph in watt per meter square per nanometer. We read those values from the graph. The value at 400 is 1, then you have 1.15, 1.25 at 500 nanometer, then 1.28 at 550 nanometer, then you have 1.3, 1.22, 1.15 at 700 nanometer, then you have 1.05, 0.8, 0.67, 0.5, 0.2 at 950 nanometer, then 0.65, 0.55 and again 0.5 at 1100 nanometer. And now we need to find out how much is the total energy incident at each wavelength. Now that is quite straightforward. So the energy incident on a given wavelength will be the spectral intensity in watt per meter square per nanometer multiplied by the area of the solar cell. In this case it is 4 centimeter square. So you convert that into meter square because the spectral intensity values are in SI units. So the area will be nothing but 4 into 10 to power minus 4 meter square, and that multiplied by the lambda range, because what we have assumed here is that the spectral intensity is a flat value in that particular range of wavelengths. So in a 50 nanometer range of wavelength we are assuming a flat value of the spectral intensity. That is why we will multiply by the lambda range. The lambda range in this example we have taken 50 nanometer as the width of the window in which my spectral intensity is constant. If I want to do it through a computer program, then I can just take each nanometer separately and then read the value for it separately and then program the computer program accordingly. Here we will take this assumption. So my energy at a given lambda is spectral intensity multiplied by area multiplied by that particular lambda range. We have taken uniform range of 50 nanometer each, those uniform slices for each of these wavelengths. So the energy comes out to be around this value. You have 0.02, then you have 0.023, you have 0.025, then 0.0256, then you have 0.026, 0.0244, 0.023, 0.021, 0.016, 0.0134, 0.01, 0.004, 0.013, 0.011 and 0.009. So we got the total energy incident on each of those wavelengths. Now basically if you look at the external quantum efficiency formula, you have the number of photons in the numerator. Now we have got the total energy incident at each wavelength. To get the number of photons, I need to find out the energy of each photon. So the next column I will make is energy of a given photon, again in watt here. So or rather the energy of the photon is usually having the units of joule. So the energy of photon I will write that as, let me write it somewhere here. So the energy of photon is nothing but you have hc by lambda, right, that much joules, or in other words I can say this is the your watt second. So and we know that h is equal to 6.63 into 10 to power minus 34 in SI units, and your c is nothing but 3 into 10 to power 8 meter per second. So we use those values of h and c, and then lambda values are given here, and if you put everything in SI units you get these values in watt second for energy of the photon, something like this, 4.95 into 10 to power minus 19, then you have 4.4 into 10 to power minus 19, 3.96 into 10 to power minus 19, 3.6 into 10 to power minus 19, 3.3 into 10 to power minus 19, 3.05 into 10 to power minus 19, and so on. You can fill the column here, and then you get to the number of photons, NPH, number of photons incident, that is nothing but your number of photons is the total energy incident at a particular wavelength divided by the energy of one photon. And because your energy of each wavelength we are taking in watts and your EPH, energy of each photon, is in watt second, so you will get number of photons as per second. So in 1 second how many photons are impinging, that is what you will get here, and you will get values something like this here, 4.04 into 10 to power 16, then you have 5.22 into 10 to power 16, 6.31 into 10 to power 16, 7.11 into 10 to power 16, 7.88 into 10 to power 16, 8.01 into 10 to power 16, and so on. You can do that, and then once you have done for all the wavelengths, then you take the summation. So, the summation of NPH, the total number of photons incident in that entire range, that comes out around 9.07 into 10 to power 17. That many photons are impinging per second. Now, for your number of electron hole pairs, NEHP. So, number of electron hole pairs, useful electron hole pairs, we have the current given in the problem, which is 0.05 amperes, and that divided by charge of 1 electron, 1.6 into 10 to power minus 19. And as we know, we can write this current or amperes also in coulomb per second, whereas the charge of an electron is in coulombs. So, you can get the number of electron hole pairs from here, and this comes out to be 3.125 into 10 to power 17 per second. So, you got the number of electron hole pairs, useful electron hole pairs per second, you got the total number of photons impinging per second. So, the external quantum efficiency eta ext is nothing but NEHP divided by NPH, or the total summation of NPH, and this is 3.125 into 10 to power 17 divided by your 9.07 into 10 to power 17, and you can multiply it by 100 to convert it to percentage, and you get this as 34.45%. So, that is the external quantum efficiency for this particular problem, considering only those wavelengths from 400 nanometer to up to 1100 nanometer. So, that is how you can calculate the external quantum efficiency. So, thank you for joining us for today's lecture, and we looked at the concepts of absorption efficiency and quantum efficiency. In the next lecture, we will be talking little more on the reflection happening in a solar cell and how to deal with it. Thank you.